General properties of linear programming problems. Welcome, everyone. So far in our unit, we have mastered the practical side of linear programming, specifically how to translate a real-world problem into a mathematical model, known as an LPP, and how to find the solution using the corner point method. However, to truly master this topic, we need to look beyond just the how and understand the why. In this lesson, we are going to dive into the underlying mathematical properties that govern these problems. Understanding these properties is crucial because they provide the theoretical foundation for optimization. They are the reason why the methods we've been using, like checking the vertices, actually work every single time. Specifically, in this subsection, we are going to explore two fundamental properties of linear programming problems. First, we will look at the nature of the feasible region, specifically its convexity. Second, we will examine the precise location where the optimal solution is found. By the end of this session, you'll see that these aren't just rules to memorize, but logical consequences of the linear constraints we work with. 1. Convexity of the feasible region. One of the most important characteristics you need to remember for any linear programming problem is that its feasible region is always a convex region. But you might be wondering, what exactly does convex mean in a mathematical sense? Let's break that down. In simple terms, imagine a region on a flat plane. We call this region convex if you can pick any 2 points. Let's call them point P and point Q, anywhere inside that region, and draw a straight line segment connecting them, and that entire line stays completely inside the region. On the other hand, if you can pick 2 points inside a shape, but the straight line you draw between them passes through the outside or empty space of the shape at any point, then we call that region non-convex, or what you might have heard called concave. Now you might ask, why is it that in an LPP, the feasible region is guaranteed to be convex? Well, think back to how we build these problems. In a linear programming problem, the feasible region is created by the intersection of several linear inequalities, something like a times x plus b times y is less than or equal to c. Each one of these individual linear inequalities defines what we call a half-plane, essentially, one side of a straight line. Now, a single half-plane is inherently a convex set. Here is the key mathematical principle. The intersection of any number of convex sets is also, itself, a convex set. So, because our feasible region is simply the overlapping area, the intersection, of multiple half-planes, which are our constraints, the resulting shape must, by definition, be a convex region. This brings us to our next slide, where we will see how this property helps us locate the optimal solution. Now that we've established that we are moving beyond just solving problems and looking at the underlying theory, let's dive into our first major property. 2. Location of the optimal solution. Now that we have established that our feasible region is always a convex shape, let's move on to our second fundamental property. This property is incredibly important because it tells us exactly where to look when we are searching for the best possible answer. Specifically, it concerns where the maximum or minimum value of our objective function, z equals a times x plus b times y, actually occurs. Let's look at what we call the vertex property. When you are working within that shaded feasible region we discussed in the previous slide, you don't need to waste time testing every single point inside the area. The optimal value of our objective and objective function is not found randomly somewhere in the middle of the region. Instead, it is always located on the boundary of the region. More specifically, if an optimal solution exists, it must occur at one of the vertices, which you might know as the corner points, of the feasible region. This is exactly why the corner point method we learned earlier is so effective. However, there is one special case we must be prepared for, which is the case of multiple optimal solutions. While it is very common for the optimal value to occur at just one single vertex, it is possible for the solution to be more than just a single point. Imagine if you have 2 adjacent corner points, let's call them point A and point B, and you calculate the value of z for both, and they yield the exact same optimal value. If that happens, then every single point on the straight line segment connecting point A and point B also yields that same optimal value. In this specific scenario, the linear programming problem doesn't just have one answer. It has infinitely many optimal solutions, all of which lie along that specific edge of the feasible region. As we will see in the next slide with our bakery example, understanding this helps us see how these mathematical rules apply to real-world production decisions. Real-world application example, production planning. Now that we have established the theoretical definitions of convexity and the vertex property, let's move away from abstract math and look at a practical, real-world application. This will help you see how these properties actually guide decision-making in business. Imagine we are looking at a small-scale business scenario, a local bakery. In our scenario, the bakery produces two main items: cakes, which we will represent by the variable x, and cookies, which we will represent by the variable y. Of course, the bakery can't produce infinite amounts. Their production is limited by specific constraints, namely the amount of flour available and the total oven time they have in a day. Let's break this down into 3 steps. First, let's look at the constraints. When we plot the limits for flour and oven time on a graph, these linear inequalities create what we call a feasible region. For example, if a constraint is written as 2x plus 1y is less than or equal to 10, it creates a straight boundary line. Because all our constraints are linear, the resulting shaded area on your graph will be a convex polygon. To put this in plain English, if the bakery has enough resources to produce 2 cakes and 5 cookies, and they also have enough to produce 4 cakes and 2 cookies, then any production combination that falls on the straight line between those 2 points is also physically possible. There are no gaps in our possibilities. Step 2 is the objective function. The bakery isn't just producing items for fun, they want to maximum their profit. We can represent this profit, which we'll call z, with the equation z equals 500x plus 100y. Our goal is to find the values of x and y that make z as large as possible. Finally, let's look at step 3, applying the properties we just learned. First, applying property 1 or convexity. The bakery manager knows that their production possibilities form a smooth, convex shape. There are no indentations or holes in this region, meaning the set of possible production plans is continuous and predictable. Second, applying property 2 or the vertex property. This is where the math saves us time. To find the maximum profit, the manager doesn't need to test every single possible combination of cakes and cookies inside that shaded area. Based on the property we discussed in the previous slide, they only need to check the corner points. Specifically, the vertices where the flour constraint line and the oven time constraint line intersect. However, we must keep that special case in mind. If the profit margins for cakes and cookies happen to be perfectly proportional to the resources they use, the manager might find that 2 different corner points yield the exact same maximum profit. If that happens, any production mix along the straight line segment connecting those 2 corners will also result in that same maximum profit. So, as we move to the next slide, keep these practical implications in mind, as we will discuss some common pitfalls students encounter when applying these rules. Common mistakes to avoid. First, let's talk about searching inside the region. A very common mistake beginners make is assuming that the optimal solution, the maximum or minimum value, could be located somewhere in the middle of the feasible region. I want you to remember this clearly. You don't need to check the interior. As we discussed in the previous slides regarding the vertex property, the optimal value will always occur on the boundary, specifically at one of the vertices, or in some cases, along an entire edge. Second, be careful not to confuse convex with curved. When we talk about a convex region in linear programming, it doesn't mean the lines are curved or rounded. In fact, as we saw in our bakery example, the boundaries are always straight lines. The term convex simply refers to the fact that the shape bulges outward and that any line segment connecting 2 points stays within the region. It is a property of the shape's structure, not the curvature of its edges. Finally, do not fall into the trap of assuming there is always only one single optimal point. While we often find a single vertex as our answer, Remember the special case we covered earlier. If the line representing your objective function, such as z equals a times x plus b times y, happens to be perfectly parallel to one of your constraint lines, you won't have just one solution. Instead, you will have infinitely many optimal solutions lying all along that specific edge. Now, before we wrap up our session, I want to pause and highlight some common pitfalls. As you move from solving basic problems to more complex optimization tasks, it is very easy to fall into these 3 traps. Keep these 3 points in mind as you practice, and you will avoid the most frequent errors in linear programming. Key takeaways. All right, we have reached the end of our lesson. Before you move on to your practice problems, let's quickly recap the 3 essential pillars we've covered today regarding the properties of linear programming. First, let's revisit convexity. Remember, the feasible region of any linear programming problem is always a convex region. What does this mean in practice? It means that if you pick any 2 valid solutions within your shaded area and draw a straight line segment between them, every single point on that line will also stay within the boundaries of your feasible region. There are no indentations or holes to worry about. Second, we have the principle of vertex optimality. This is the most practical rule for solving these and problems. When you are looking for the maximum or minimum value of your objective function, z, you don't need to test every point inside the shaded area. The optimal value is guaranteed to occur on the boundary, specifically at one of the corner points, or vertices, of the feasible region. This is exactly why the corner point method we learned earlier is so effective. Finally, keep in mind the possibility of infinite solutions. While we usually find a single optimal corner point, don't be surprised if you encounter a case where 2 adjacent vertices yield the exact same optimal value for z. If that happens, it means the entire line segment connecting those 2 vertices is also optimal, giving you infinitely many solutions along that edge. Keep these 3 points in mind, as they form the theoretical foundation for everything you will do in optimization. Great job today!